Hello, my name is Joel Rivitsky. In this video, I will talk about our recent work on fast graphical population protocols. This is joint work with Dan Alister and Rati Gelashvili. Population protocols model distributed systems consisting of computationally restricted entities that interact in an unpredictable manner. In this talk, we consider computation in structured populations where the structure of the population is given by a graph. Each node in the graph corresponds to a single agent that is modeled as a finite state automaton. The computation proceeds asynchronously via pairwise interactions, but only nodes that are connected by an edge in the graph can interact with each other. Nodes that are not connected by an edge can never directly interact. We assume that initially all nodes are indistinguishable, that is, there are no unique identifiers. However, the nodes may receive some local input depending on the distributed tasks we are trying to solve. There's a vast body of work studying what problems are solvable in the population protocol model. Today we focus on the following question: how fast global coordination problems can be solved on graphs. In order to talk about time complexity, we consider a stochastic version of the population protocol model. In this model, interactions between nodes are dictated by a stochastic scheduler. First, each node initializes its state according to its local input. Then in each time step, the scheduler chooses an edge uniformly at random. After this, the nodes connected by this edge exchange information with each other, for example their current states, and then update their local states. The update rules used by the nodes are specified by the population protocol the nodes are running. In the next step, a new edge is again sampled, and the nodes connected by this edge will interact and update their local states. And so on. This process runs forever. The scheduler keeps on selecting edges at random, and the nodes keep interacting with each other. In each step, every node produces some output by mapping its local state to an output value. We say that the system reaches a stable configuration if the outputs of the nodes do not change, no matter which sequence of interactions the scheduler picks in the future. The set of stable configurations, of course, depends on the problem at hand. We are interested in designing algorithms that always eventually reach a stable configuration. Note that we do not assume that the protocols have to deal with arbitrary initial states. That is, we are not today dealing with self-stabilizing algorithms. We measure the efficiency of an algorithm using two complexity measures. First, time complexity is the expected number of steps until a stable configuration is reached. Often, one also considers parallel time, which is simply the expected number of steps divided by the total number of nodes in the system. Space complexity is the maximum number of distinct states used by any node in the system. Today, we focus on the leader election and the majority tasks. In the majority task, each node is given one of the two colors, blue or red, as input. The task is to determine which of the input colors was initially held by the majority of the nodes. So if the majority of the nodes are initially blue, then all nodes should eventually output blue. If red is the initial majority opinion, then all nodes should output red. So in a stable configuration, all nodes output the majority value. The second problem we consider is leader election. In this problem, there is no input. The task is to select exactly one node as a leader who outputs a special value indicating that it's a leader. All other nodes should output a value denoting that they are not the leader. Note that in a stable configuration, the same node remains the leader no matter what interactions follow. Okay, so let's talk about what's known about the complexity of these problems and how our new results relate to the prior work. A vast majority of the work studying complexity of leader election and majority has focused on the case where the interaction graph is a clique. In a clique, any pair of distinct nodes are equally likely to interact in any given step. This essentially corresponds to assuming mass action kinetics in a well-mixed systems. You can think of this as putting a bunch of molecules into a test tube and shaking it vigorously so that the molecules bump into each other in a random way. In this work, we go beyond the well-mixed setting and instead consider spatially structured systems. Now the situation is quite different, as the interaction patterns now depend on the structure of the underlying interaction graph. This makes the analysis of many protocols much more challenging. Let's now overview what's known about leader election and the majority problem in both the well-mixed and the spatially structured setting. The case of leader election in the click is pretty much settled. Doty and Soloveitchik showed that any constant state protocol must use linear parallel time or quadratically many steps in expectation to solve leader election. And this is tight for constant state protocols. However, if you allow the number of states to slowly grow as a function of the total population size n, then it's possible to get much faster algorithms. After a series of improvements, it's now known that in the click, you can elect a leader using log n many states in only logarithmic parallel time. In general graphs, a 6-state protocol solves leader election in polynomially many steps in any connected graph. In this work, we show that in regular graphs with high conductance, you can actually stabilize much faster, almost as fast as in the click. For example, in graphs with constant conductance, such as constant degree expounder graphs, it's possible to solve leader election using polylogarithmically many states in polylogarithmic parallel time. Of course, our results extend to non-constant conductance. The dependence on conductance is quadratic. So, if the graph has good expansion properties, then we get fast and space-efficient protocols for leader election. The story for majority is fairly similar. There is a trade-off between the number of states the protocol uses and the time it takes for the protocol to stabilize. Constant state protocols are again slower, but if you let the number of states depend on the population size, much faster algorithms exist. Very recently, Doty and others showed that leader election can be solved in logarithmic parallel time using only logarithmically many states. And this is known to be optimal for a large class of protocols. In the graphical setting, Drayev and Vojinovic have shown that a 4-state protocol stabilizes in polynomially many steps. Similar as in the case of leader election, we show that in regular graphs, majority has both parallel time and space complexity of at most 1 over conductance squared times polylog n. So again, in graphs with good expansion properties, we obtain efficient algorithms for majority. Okay, so let's briefly talk about how we get these upper bounds in the spatially structured setting. Since dealing with arbitrary graphs is a bit messy, we instead simulate a nice synchronous click model in the asynchronous population protocol model on graphs. While we focus on regular graphs for convenience, we are confident that the basic approach generalizes to non-regular connected graphs. This nice model we simulate is not exactly the same as the well-mixed population protocol model, but it's close enough so that we can adopt techniques developed for the population protocol model in the click to our new model. So what is this nice model exactly? We call it the k-token shuffling model, where k is a parameter of the model. In the following example, the parameter k is set to 2. As before, n denotes the number of nodes, that is, the size of the population. The computation in this model proceeds as follows. In each synchronous round, every node in parallel generates exactly k tokens based on its current state. Thus, a total of n times k tokens are created in one round. After this, the tokens are shuffled and distributed back to the nodes so that every node gets exactly k tokens. In other words, we permute the tokens uniformly at random. Finally, each node updates its local state according to its current state and the tokens it received. The k-token shuffling model can be simulated in the stochastic population protocol model on graphs. The k-token model is much easier to work with as it's a synchronous model without any spatial structure. So we can simply design an algorithm for the k-token model and run it in the graphical population protocol model and avoid all the complexities of dealing with the structure of the underlying interaction graph. So how is this simulation done? The basic idea is very simple. Nodes generate their tokens, and then we just randomly shuffle these tokens using a shuffling protocol in the population protocol model. After we've shuffled the tokens for long enough, we obtain a random permutation that is statistically close enough to a random permutation chosen uniformly at random. The main challenge is of course implementing and analyzing this shuffling protocol. First, we need to determine how long it takes to shuffle the tokens under the stochastic scheduler. To do this, we analyze a variant of the classic interchange process and bound the mixing time of this process using the expansion properties of the underlying interaction graph. In the classic interchange process, each node holds a single token, but we consider an extension where each node holds exactly k tokens instead of just one. Second, the nodes need to know when to stop the shuffling and when to switch to a new round. For this, we use a distributed phase clock to synchronize the nodes. Putting these ingredients together requires a bit of work, but that's the gist of it. The details are given in the full version of the paper. So that's how we get new upper bounds for majority and leader election on graphs. Our simulation technique is of course not restricted to just these two problems. You can pick your favorite k-token shuffling model protocol and run it in the population protocol model on graphs. Now, while our analysis is only for regular graphs and assumes that the nodes have access to some random bits as well, it seems likely that this general simulation idea can be extended to non-regular graphs as well. I invite you to take a look at the full version of the paper available on arXiv. Thanks for listening.